I want to talk about work. Let us see how much work do you do? Section 7.5. So in this section we consider first the elementary idea of work. That is the work that is produced from a spring. And so here we use Hooke's law. Hooke's law says that the force required to compress or stretch a spring is directly proportional to the distance of the stretch or the compression. So the force produced from the stretching or compressing spring is directly proportional to the distance of the stretch. Thus, the force is equal to some constant times x, where F is the force, K is some constant of proportionality to be determined, and x is equal to the distance of the stretching or compression. Now we define work. Work is simply the force that is required to move an object some distance that we call d. We can look at this work as the change of the force times the distance, or the force times the change in the distance. Note that it may be necessary at times to consider weight as the force. If you have a liquid going into a tank and you're trying to fill the tank or you're trying to empty the tank, we talk about the weight of the liquid as the water or whatever liquid it is being filled into the tank or emptying out of the tank. So if that's the case, then this weight is calculated by the volume times the weight density of the liquid. According to calculus, we define work in this way, that work, we say W, is no more than just the integral from A to B. A to B is the distance that's been covered of some force, F of x times dx. Well, please note here that F is the force, may the force be with you, and dx is the distance. So we get work. Now let's look at a few problems. I only want to work 4 of these problems, and then I must go home. I will decrease, if you will. Consider number 5. There you want to use Hooke's law to determine the variable force in the spring problem. It says a force of 5 pounds compresses a 15-inch spring a total of 3 inches. So here x is equal to 3 inches. We use Hooke's law, that is F is equal to some constant times x. In doing so, this implies that we have 5 is equal to 3 times k. Well, here we can solve for k, the constant of proportionality that is to be determined. Here we have determined it. Now from there, the force now is 5/3 times x. But you're looking for the work. So the work here is the integral. It says further how much work is done in compressing the spring 7 inches. So we're going from 0 to 7. 5/3 times x dx. So we get 5/3 times x to the second divided by 2. This is evaluated from 0 to 7. So we get 5/6 times 7 squared. So that gives us 49 times 5, 245 all over 6. And we measure the work in the weight or the force times the distance, so, or the distance times the force. So here the distance is in inches and the force is in pounds. Number 7, a force of 250 newtons stretches a spring 30 centimeters. So x is equal to 30 centimeters. How much work is done in stretching the spring from 20 centimeters to 50 centimeters? So here we look at Hooke's law, and in that we have 250 is equal to 30 times k. This implies that k is equal to 25/3. So the force formula is given as 25/3 times x. So now we integrate to find the work. This is the integral. Here we're going from 20 centimeters of the stretch to 50. How much work is done in stretching the spring from 20 centimeters to 50 centimeters? So we have 25/3x dx. So this gives us 25/6 times x squared. Evaluate this from 20 to 50. And when we simplify all of that, that gives us 8,750 newtons centimeters. you see that this is simply 25 over 6 times 50 squared minus 20 squared. And that's what you get. Let's look at some more problems here. Let's look at some problems where the work is not required by some spring, and so we don't use Hooke's law. Look at number 17. This is a problem dealing with pumping water. Here, a rectangular tank with a base 4 feet by 5 feet and a height of 4 feet is full of water, and they have a figure there that you can look at. And I would try my best to draw it out, but please don't quote me on that. You thank God for the image in the book, right? So this is 5 feet here, 4 feet there, and then 4 feet going up. And so you're pumping water. The water weighs 62.4 pounds per cubic foot. That's the weight density of water. How much work is done in pumping water out over the top? Part A, to empty half of it, then part B, to empty all of it. So we got water being pumped out. I don't like that tip right there. I'll just leave it like that. I don't want to mess up the drawing. Got it looking so nice. So, part A. Here we're looking for the so-called work, and this is the integral. Since this is fluid, I need to talk about the volume. That's going to give me the so-called weight density. Of the water times here. I need a few things to get the volume. I got to have the length, the width, and the height. So if this is the so-called length, and if this is the width, then this guy here is the height. But hold on with the height, because the height is changing because we're filling this guy up or we're emptying it. So this guy is changing as the water is pumped out. So here H has this form, 4 minus Y, where Y is considered to be moving up and down the y-axis. Okay, so I have 5 times 4 minus y. And to empty half of it, so we're going here from A to B, if you will, or C to D. So I'm going from 2 to 4. This is to empty half, right? So I have the weight density, 62.4 times the 5 times the 4, that's 20, and then times 4 minus y dy. So let's bring it down here. Well, I can put it here. So the work is, let's bring out all the constant terms. The integral from 2 to 4, 4 minus y dy. And so this is 62.4 times 20 times 4y minus y squared all over 2. Evaluate that from 2 to 4. So we have 62.4 times 20 times 16 minus, evaluate the y's at 4. So that's 16 minus 16 divided by 2 is 8. And then minus 62.4 times 20. Now evaluate the y's at the 2. We get 8 minus 4 divided by 2 is 2. So we have 62.4 times 20 times parentheses 8 minus 6. So that gives us 2 times 20, 40 times 62.4. And so we calculate that. That gives us 2,496, and that's in foot pounds, or pounds foot, however which way you like to say it. Now part B, they want you to empty all of it, so the integral just goes from 0 to 4. So the work 62.4, you got the 20 out there, and I go from 0 to 4, a 4 minus y dy. Well, all we do is just, we got the results, so this is 62.4 from part A, that is, times 20, and we just take the first part, because that was evaluated at 4, evaluated at 0, and we get 0. So this is 62.4 times 20 times the 16 minus 8, or times 8, and then you calculate that, and you get 9,984 foot-pounds. Now let's consider one more problem there, number 19. Again, you're pumping water. A cylindrical water tank 4 meters high with a radius of 4 meters is buried so that the top of the tank is 1 meter below ground level. How much work is done in pumping a full tank of water up to ground level? And the water here weighs 9,800 newtons per cubic meter. So the weight density in the metric system is 9,800 newtons per cubic meter. This is for water, so we need that. And you can look at the image there. They give us the height is 5 minus y. We look at the image that's given. Now you want to calculate the volume for this so-called cylinder. But this is, the formula is pi r squared times the height. So this volume is pi, and the radius is given to be 2 squared times the height. This is 5 minus y. So the work now is the weight density, which is at 9,800 out in the front, times some integral. Here we have pi times 4 times 5 minus y dy. Now, in terms of the integration and what we're going to integrate, it says that the cylindrical water tank 4 meters high, the tank's only 4 meters high, so you can only fill it or empty it up to that particular point. Is 1 meter between the tank and the ground level. So here, in terms of the tank, we integrate from 0 to 4. And so work, let's simplify this. This is 9,800. On the outside, we got 4 pi integral from 0 to 4, 5 minus y dy. We integrate 4 pi times 9,800 times 5y minus y squared over 2. The y evaluated from 0 to 4. So we have 4 pi times 9,800 times 5 times y, that's 20, minus 16 divided by 2, that's 8. So we get 12 times the 4y 12 times the 4 pi, excuse me, times the 9800. So we get 48 times 9800, and that gives us 470,400 Newton meters. Okay. Well, I hope you are pleased with that. Thank you.